Oh. On A. Okay, cool. So, IM forces, long and short of it, is that so between atoms, or rather within atoms, right? Within atoms, there are forces, but even between an atom and an atom in a molecule, there are also forces that keep them together. And also between molecules. So, between the water molecules, there's forces. Ka acid, alcohol, coffee. There's forces in between the atoms in the substance. That's one. Two, the forces between atoms are called interatomic forces.
Okay.
And the forces between molecules are called intermolecular forces. So inter as a prefix, like that which you put before a word, then becomes between stuff, right?
Yes.
So between atoms is interatomic and between molecules is intermolecular. Right. So okay, chemical bonds. So why do atoms combine? It's because the same topic we just had are valence electrons, right? Some atoms are willing to donate electrons, some are willing to receive electrons. And because there's that, there'll always be chemical reactions. It's just as some people are willing to find purpose and meaning in life, so they'll work a job as a professional in this industry.
Okay.
Or some people believe that they will make great wives, so instead of pursuing an education, they'll become that. Other people believe that, hey, you know what, I'm going to be a cop because, others will say, I'm going to be a lawyer because, others will say, I'm going to be an engineer because. So because there's always those things, having professionals or having people fill certain roles in society will always happen.
Okay.
Elements, it's the same thing. Because there's always a valence electron, if you are not in group Eliamafeller, Eddie Noble gas, there's likely to be a reaction. That's what that means, right? So we talked about the energy levels, etc. But now, how bonds form, right? There are two cases we need to consider when two atoms come close together. So when atoms approach each other, what happens? The first case, they bond. Yay! And in the second case, what happens? They can come closer, but they won't bond. Yeah, one. So that's the part I was referring to say some elements, you just put them in a cup together and they'll react. You put inogar rames, you get that psh.
Yes.
Yeah. But some, you just combine them and they'll never mix. That stone is not going anywhere. It's just going to be in the water. And that's because even though water and the stone is made of a mineral, which is a chemical, effectively, just because the atoms are close together on a surface level, at the surface of the stone, the water and stone are in contact, doesn't mean there's a reaction. It just means ibile water has that property of sticking to things. It's called cohesion, adhesion. I'm not sure, but capillarity is also another variant of that. Yeah, but nevertheless, water has a property of homarel. Yeah, water has a property of homarel. Have you seen a physical thermometer? That thing of water temperature. Have you seen it move up and down a thing?
Yeah.
Have you seen at the top of that in Kaila? It's round like this.
Yeah.
If you put the same amount of water in a similar thing, it does the opposite. That's called a meniscus.
Okay.
So for mercury doesn't stick to a surface.
Okay.
It just rolls over it. Like a chair, like imetsi, marawi, imetsi, asimetsi, imetsi, marawi cello, so it just rolls anyway. A color. But that's because it doesn't have that property to stick to things like water does. So that's why I got a straw. No level la momenti afelang karadile sea salt.
Yeah.
But if it were mercury, it would do this. It would cup like that. So the meniscus are different. So in the case of water coming into contact with stone, just because the atoms are close together doesn't mean that they're bonding. It's a kind of similar thing with mercury and the thermometer. Just because they're close together doesn't mean they're bonding. Yeah. So when a bond forms, these atoms move closer and closer and closer together. So the first thing that happens is repulsion. Do you know what repulsion means? I don't know. Repulsion comes from the word repel. You know what to repel is?
I think. Maybe.
To repel is to hot your magnet. Or venture south to south. Yeah. But our venture north and south here attract. So repulsion is that property to keep away, push away. So in English you I don't know what the transformation is called, but another word you can make from repel is repulsion, which is that which shows repelling.
Okay.
Yeah. So because the atoms are coming into contact with each other, let's say it's hydrogen atoms, because you have a molecule, that H2, which is made of 2 atoms of hydrogen. Right?
Yeah.
So H2 is H plus H, right? So because they have the same structure, proton 1, neutron 1, electron 1, as they get closer, the electrons repel each other. The electrons will push each other away. So now I'm thinking what happens is, maybe let's say electron repel here, and then this electron goes the other side. That means then the one electron gets closer to the other to the other atom's nucleus, which is positive. And when that happens, then the second thing happens, which the negative of the one attracts to the positive of the other. All right? And then what then ends up happening is, now that these two are close together, you find that the atoms are so close now, they are whole. But now the positives start repelling each other.
Okay.
You know, so that's what happens. So these 3 forces work together when the 2 atoms come close together. And as the total force changes, the amount of energy in the system also changes. And this is what happens, right? So when the distance between the nuclei is small, the energy change, there's a drop in energy change, right? At the lowest energy level, you get your atoms. To understand, let's discuss this graph here. So still under 1, our graph looks something like this. And it goes like that. So let's imagine that we have fixed the one atom, and we'll move the other atom closer to the first atom. So we're picturing a scenario where we've got 2 atoms. One is fixed, then the other we move like that, right? So as we move the second hydrogen closer to the first, that is from point A to point X. So point A is there, and point X is there. I'll just write black now. X, that's A. So that's 0 plus minus. Okay. So we start from point A, and we're moving our atoms closer and closer. So our atoms are like this. Ne? And then we move them closer. Right? Now as we move them closer, what happens to the energy? The energy drops. And at its lowest, that's when there is a bonding. Alright? That's when there is a bonding. That's when there's a bonding. So now, further towards the left of point X, so in other words, if we move more this side, if we move more towards this side, then what ends up happening is the repulsive forces are stronger than the retractive forces, and the energy of the system increases. Alright, so for hydrogen, the energy at point X is low enough that the two atoms stay together and don't break apart. This is why when we draw the Lewis diagram, we always show an electron pair between them. So here, we illustrate hydrogen, hydrogen. One has an X, one has a dot. But this here illustrates our molecule H2. Two. In the second case, a bond doesn't form, right? So if we look at helium, we see that each helium ion has a filled outer energy level. Right? So on our periodic table, helium, the energy level on the outside is filled. So when we look at this graph, we find that the energy minimum for two helium ions is very close to 0. This means that the two atoms can come together and move apart very easily and never actually stick together. So what that looks like on this same graph here, energy level versus distance between nuclei, is that this would be plus, minus, and this point X. So the atoms would be very close to each other here, but because there's no attraction between the atoms, then there's no bonding. So, and it's also easy to just move them between and apart. So there's no bond. So Lewis diagrams also correspond with electron configuration and valence electrons. And this table here shows that. I think I shared with you this link to this learning guide in Classroom. You don't see it. Let's check. Classroom. It's grade 11. I think I should have shared with you. I shared this with everyone. People. Let's see. Oh, it's the other email. Okay, fair enough. 9-day 5-6. Okay, cool. So then you'll have access to this class. Alrighty. Whew. Yes, there we go. Alright, so remember these electron configurations, ne?
Yes.
1s2, 2s2, 2p6, etc. the valence electrons also correspond to how the Lewis diagrams look. So beryllium, which is in group 2, like calcium and magnesium, will have like this. Hydrogen, lithium, sodium, potassium will be like that. Boron and the other ones in the group, carbon, nitrogen, and oxygen, fluorine, and neon. So all of those, they'll always have 2, 2, 2 on either side like this. Alright. And then what else did you say you wanna get better at?
The effects of intermolecular forces. Yeah.
Intermolecular forces, yes, because we were still getting to that, yes. Okay, so Lewis diagrams, can you do them?
Yes.
Okay, cool. So if you know how to identify Lewis diagrams with Maragin Trelani, your groups, Jamo periodic table, and you know how to draw them, then you should be fine. Can I quickly go to the bathroom? Yeah, what?
Let's see.
Alright, so intermolecular forces. Okay, so those diagrams, you can move past, you can move past, you can move past. Okay. Alright, this thing, Jabo, electronegativity and bonding. Let's start there. Remember we talked a little bit about electronegativity? Alright, so we've looked at covalent molecules, but how do we know that they are covalent? We know that they are covalent because of their electronegativity. So we literally went to the same chapter but in grade 10, but now in grade 11 it's just added a couple more layers.
Yeah.
You see?
I see.
So we're learning the same thing from grade 8. We just keep adding stuff to it and making it more complex and more complex and more complex. And that corresponds to our development as humans. Every year when we grow, life throws at us situations, incidences, happenings, etc., experiences that grow us from where we were before to another level.
Yeah.
So with our learning, it's the same thing.
Okay.
Yeah. It's just that sometimes life will kind of like, this and that, and then you can't focus and you don't see the point in school. Yeah. But just always when you're in your class, always think about it from a broader perspective. So electronegativity. Electronegativity. Alright, cool. So it's the measure of how strongly an atom pulls a shared electron pair towards it, right?
Yes.
And this tells us whether or not an atom is covalent. Okay. Wait. What? What does it say? how strongly an atom pulls electron pair towards it. So we'll say so how strongly an atom pulls a shared electron pair towards it. All right, and this also tells us whether or not the molecule is covalent. This tells us okay. On this periodic table, the fullest, see that in the front of the book on the periodic table, top right corner. Okay, cool. Let's look at the electronegativity. So page 150, 166 there. Let's look at the periodic table quick because they're giving us something to reference there. All right. So, En, electronegativity. See the number there? So on each of these atoms, there's an electronegativity. The smallest is there, and the highest is there. Remember, francium, fluorine, from 0.7 to 4. So electronegativity increases this way, right? They even look the same, even though they have different AMU and numbers. Yeah. So that's the electronegativity. That's one. So we know that the more you go this side, the higher the electronegativity, and if you go this side, the lower the electronegativity. Now we're gonna refer to that. What is it? Yeah. Okay, cool. So these are some electronegativities of select elements. Sharp. Now we're gonna calculate electronegativity differences, right? So between hydrogen and oxygen, we're gonna work out the electronegativity, right? So from the periodic table, the electronegativity of hydrogen is 2.1, and the electronegativity of oxygen is 3.5, right? So the electronegativity difference would be 3.5 minus 2.1, which is 1.4. This is the En difference. All right. So once we're able to work that stuff, right, we then have something called an okay, so once we know how to do this difference in electronegativity, then we can determine the type of bond that comes up just because we know the electronegativity.
Okay.
So if we have like AR 1.4, so it's between here, so that means it's going to be a strong polar covalent, just by working out those two things.
Okay.
Yeah. So now we know the bond between hydrogen and water is a strong polar covalent bond.
Yeah.
Because the electronegativity difference between them ranges 1.1 and 2. Alright.
Yeah.
If we take sodium, and electronegativity of chlorine. Okay. Let's quickly look. 68. Chlorine has got 3.0 and sodium inale 0.9. So if we take the difference, it's going to be 3.0 minus 0.9, which is 3.1, which is larger than, what was the threshold? After 2K. Yeah, so after 2, it's ionic. So you can get given any compound, right?
Mm-hmm.
Let's say it's water, it's sodium chloride, it's hydrochloric acid, it doesn't matter. You can get given any compound or any molecule, and if you know the electronegativity of the atoms, then you can determine if the type of bond between those is nonpolar, weak polar, strong polar, or ionic. And it's a very simple calculation. It's very straightforward, that one. So it's important to be able to determine if a molecule, and this is why, so this now extends our conversation here, electronegativity. So now that we know our electronegativity scale is 0, 0.1 to 1, 1.1 to 2, and 2.1 and above, right? So we've got a scale here. This here is non-polar. If it's 0, it's non-polar. And if it's in this range, it's weak polar. It's got a polar bond, but it's weak. If it's in this range, it's stronger and it's polar. And above 2.1, it's ionic. Not ironic, ionic. So non-polar versus polar bonds. Let's start here. Agree on our scale, we had non-polar. So now we're comparing polar and non-polar. But all polar, in polar we've got weak and strong.
Okay.
Yeah. So not everything is in black and white in science. There's always something for everyone. Yeah. So with polar, I'll just write here covalent bonds because yeah, if I don't, it'll be something else when I read it again. Covalent bonds. Okay, cool. So we can use now electronegativity to explain the difference between two types of covalent bonds. And non-polar covalent bonds occur between two identical non-metal atoms, right? So between two identical non-metal atoms. So this is your hydrogen, oxygen, nitrogen, chlorine gas, etc., right? Because these two atoms have the same electronegativity, the difference is 0. Remember that electronegativity calculation we were just doing now? Obviously, if you take the bigger one minus the smaller one, we get an answer. And that answer, we either say it's 0, between 0.1 and 1, 1.1 and 2, or 2.1 and above. Remember that?
Yeah.
So because of that calculation, if we take the electronegativity of hydrogen and we subtract the electronegativity of hydrogen, we get 0. Because the electronegativities are equal. Alright? So that's because En of hydrogen minus En of hydrogen is 0. Alright? So this we can keep in mind. Alright? But if two different non-metal atoms bond, then the shared electron pair will be pulled on more strongly by the atom with a higher electronegativity. So in other words, an atom that has a high electronegativity is more likely to pull electrons towards it.
Okay.
It's more receptive of electrons. So because of that, and its high electronegativity, chances are it'll form a polar covalent bond. Right, so non-metals, so higher En atom pulls electrons from lower En atoms, electronegativity atom. So yeah, the shared electron pair will be pulled more strongly by the atom with a higher electronegativity. And then this results in polar covalent bonds. So slightly positive or slightly negative charges are called partial charges. And these are represented using, I guess, delta positive and delta negative to show that something is slightly positive and slightly negative. And how they illustrate this in parts of this particular learning guide is that if you have a molecule, what we call water, let's say here, right? So the part that has more oxygen, or rather the part that is the oxygen part, if you look at this in a like a division somewhere, where the parts closest to hydrogen would be more positive, and the parts closest to oxygen would be more negative. So that's why they do that, and that's why they do that. So if you want to imagine it as a simplified diagram, if we say how the atoms look or how the sizes compare, you can just say on the one end it's positive and on the other end it's negative. Yeah, so that's the long and short of it, right? So in other words, in HCl, the H has got a, and the Cl has got a negative there. Then we have polar molecules. So, oh no. So polar, so we had polar covalent bonds and polar and non-polar covalent bonds, I guess. So now we've got non-polar molecules, and the difference is molecules. This is bonds. The other one was bonds, yes, covalent bonds. And this one is polar molecules. All right, so polar molecule has one end slightly positive and one end slightly negative. So basically, one end slightly positive and one end slightly negative. And then non-polar, oh okay. Yeah, so polar, what did I do here? Okay, I see what I did. My mistake. So in the column, the first column, that's your polar molecules. Since I've already discussed properties are the polar molecules, which would be one end slightly positive and another slightly negative. But non-polar would have one charge equally spread across, right? So one charge spread across the molecule, and or symmetrical molecule with polar bonds. Or, do you know what symmetry means? Oh, okay. Symmetrical molecule with polar bonds. All right. So yeah. Okay, so let's do a couple of these questions. Just so we reinforce hore, we've been learning something, yeah? Alright, so state whether H2 is a polar or non-polar molecule. Okay? Determine the shape of the molecule. Firstly, the molecule is linear. There's one bonding pair and no lone pairs. So it's just flat.
Yeah.
And then the second thing, we need to write down the electronegativities of each atom. So it's 2.1, it's just hydrogen. And we read this off the periodic table.
Yeah.
And thirdly, the electronegativity difference for each bond. There's only one bond and the difference is 0. So get non-polar from our criteria. Determine the polarity of each bond. The bond is non-polar because it's one charge across a molecule. Alright. And the molecule is also non-polar. The bond is between identical non-metal atoms, so it's non-polar covalent. And then the molecule is non-polar because one charge is across the same molecule.
Okay.
Yeah. This one. This one gets different. Methane, is it polar or non-polar? The molecule is tetrahedral. So methane looks like this, right? Carbon, hydrogen, 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 hydrogen. If you want to visualize it in 3D, there's your carbon atom. There's one hydrogen. There's another. Another's at the back and another's at the top, right? And maybe not. So I'll just start with the one hydrogen in the front, the other one at the back, the one on the side, and the other one we can't really see in full. And the carbon, it looks something like this. I think the other one's supposed to come to the top like that. Yeah. Alrighty. So this shape is called a tetrahedron. Do you know how to visualize 3D shapes? You must have done this in maths. So tetrahedron looks something like this, right? Right, so you can see these two faces, but you can't see the one at the back and the one at the bottom. Similarly, that molecule is shaped like this, and at the corners of the tetrahedron is your hydrogen, right? So there are 4 bonding pairs of electrons and no lone pairs. So because carbon would receive in this case, then the hydrogens would give it. So 4 electrons will be received by the carbon. Yeah. Electronegativity difference for each bond. There are 4 bonds and it's 1 carbon to 4 hydrogens. So that means each bond has the same electronegativity. And the electronegativity difference is 2.5 for carbon minus 2.1 for hydrogen, and the difference is 0.4. Now, if it's 0.4, our table tells us it's between 0.1 and 1, so it's a weak polar molecular force or bond. It's weak polar. And then the molecule is also symmetrical, so it's non-polar. Alright, so I've added you to this. You can find the learning guide and just revise these before Mala.
Okay.
But yeah. Yo, it's 3 o'clock now.